Hi everyone, this is Matt Ingram with the continuation of Replication 3B, the replication in R of Messner et al. 2013. I'll skip the preliminaries, the overview preliminaries, and the preliminaries regarding the replication in R itself, since this is the second part of the video. In the first part of the video, we did the percentile maps in figures 1 and 2, just recalling that we're in this replication we're only reproducing the results for robbery rates. Messner et al. Analyzed both robbery rates and assault rates, but the tools and techniques are identical, so this video is focused only on robbery rates, assuming that you will be doing the replication for assault rates on your own. In the first video, we also did figure 3. We also reproduced figure 3, that is, the LISA cluster maps for robbery rates. And again, I assume that you're doing the LISA cluster map in figure 4 for assault rates on your own. In this video, we're going to turn now to step 3 here, the generating the OLS model and the spatial diagnostics that then lead us to specify the spatial error model, or SEM, in Table 1 and Table 2. Table 1 examines robbery rates, Table 2 examines assault rates. So in this video we will do the replication of the two models in Table 1, and then I'll leave you to do the two models in Table 2 on your own time. Just a reminder that the weights matrix used by the authors has a 15 nearest neighbors specification, and it's a symmetric weights matrix, so we'll need to generate that in R. You should have generated that already for the LISA cluster maps in order to do the exploratory analysis that led to the LISA cluster maps, so I assume that you already have that in memory. So let's go to the article itself and see what they have to say about their OLS model specification and their spatial diagnostics, and then we'll take a quick look at Table 1 and before getting into the R environment. So in the article itself, just a reminder that I wanted to zoom in here, that if we this is Table 1 with the first set of spatial regressions. Just a reminder that these are both spatial error regressions, so the lambda term is down here at the bottom in both models. So neither one of this is the simple OLS model. The simple OLS model would include all of the predictors in model 1 except for lambda, but this is not explicitly reported in the article. We're on page 1032 right now, but if we go back to page 1028, you'll see at the bottom the discussion of, this is page 1028, and this is the extent of the discussion of the OLS, of the OLS model and the spatial diagnostics. So the authors tell us that preliminary analyses based on an OLS model revealed that there was still some spatial autocorrelation in the residuals. That's identified with a Moran's test. So it looks like there's some clustering of the residuals. So we can reproduce those results. Here they're reporting 0.224 for robbery and 0.188 for assault rates respectively. And then they tell us that their spatial diagnostics lead them to specify a spatial error model rather than a spatial lag model. The specific tests that they used in conducting the spatial diagnostics are not mentioned here. We can assume reasonably that they're talking about Lagrange multiplier tests, but we'll conduct those tests explicitly and see if they lead us down the same path. So again, we want to use the information from Table 1 to build a simple OLS model, and then generate a Moran's I test on the residuals and run some Lagrange multiplier tests that will hopefully lead us to identify the spatial error model as the correct specification for a spatial regression. So let's go to table 1 and look at the variables that we need for the OLS model. Here we are in table 1. So our dependent variable will be the logged robbery rate. Again, in the previous exploratory analysis, we've been using the raw rate. Now we want to shift to the logged rate. And our predictors, excuse me, are some regional dummies, east and south, resource deprivation, urbanism, divorce rates, age structure, and sex ratio. The squared term for urbanism appears only in the second model, so we don't want to include that in the simple OLS model. So let's go into R and see what this looks like. Here we are in the R environment. I am using the R GUI, so if you're using the R Studio interface, things might look a little bit different, but the content of the R script is exactly the same. And here we are at step 8, at the beginning of step 8, specifying the OLS model. Here's a reminder of what our dependent variables are, the logged rates for both robbery rates and assault rates. And this is the specification for our basic OLS model. I'm just going to expand the window here so we can see the full thing. We see that the dependent variable is logged robbery rates, and then we have east, south, deprivation, urbanism, age structure, divorce rates, sex ratio, and we're referencing the data frame object of the shapefile. We're going to call our linear model shape1.lm, and let's execute this. Now we can hit Control R. Successful. You can see it's been successful over here on the left, and we can summarize that model. Now we don't need to spend too much time looking at the coefficients here in the model or the exact results of the model. We're mainly interested in running some spatial diagnostics, so let's get to that. On the way there, here are just some other commands to shorthand the linear model. You can also look at some commands here to capture the output of the model. If you run various models, you can also capture that output or combine all of the models into a single output. I also have some non-spatial diagnostics for multicollinearity, looking at some correlations or AIC values. But let's focus on the spatial diagnostics here in step 9b. So we want to specify again our weights matrix. This should be in memory, but just in case, let's just run that command again. Make sure that list W is capturing that symmetric weights matrix for 15 nearest neighbors. For some of the operations, we might need a neighbor object, so let's just make sure we specify that as well. We could run Roger Bivens' Correlogram command, just to look at how Moran's I varies across various orders of neighbors. I ran this earlier, and so we could plot what that looks like. And essentially this is what it looks like. It's suggesting that across the first few orders of neighbors there's a positive spatial autocorrelation, and after the 5th order of neighbors or so there's a negative spatial autocorrelation. It's not entirely clear that that's statistically significant, but that's an interesting diagnostic, or it could be an informative diagnostic. If you are interested in spatial regimes, you might hear some code from the previous first replication. Again, this is all from the 2001 piece by Robert Baller, Glenn Dean, Luke Anselin, Steve Messner, and others. So if you're interested in doing the spatial regime, there was a simple non-spatial version of the test. You would be interested in the spatial version of the Chow test if the Lagrange multiplier test indicated that there was some spatial autocorrelation. But since Messner et al. In their 2013 piece are not interested in spatial regimes analysis, let's focus here on the LM test, or Lagrange multiplier tests. So this is the basic LM error test. Sorry, I was going to do the Moran's I first. Where did Moran's eye end up? Here it is. Hang on just one second. Sorry, this is the first basic Lagrange error test, Lagrange multiplier error test. This is the basic Moran's test. So if we did the basic Moran's test, we get a statistic of 0.227, 0.228 roughly. Again, if we went back to the Messner et al. Piece to page 1028, they find for robbery rates a Moran's eye of 0.224. So let's come back to table 1. And we find 0.228. That's very, very, very close. I'm not quite sure why exactly there is any discrepancy at all, but they could be a different spatial weight structure, or they could be using a different distance criterion for capturing nearest neighbors or for adjudicating ties among nearest neighbors. But in any case, it's substantially similar. The basic LM error test is specified in the syntax that I just ran. It's statistically significant and has a high value. But what we would be more interested in doing, or in executing rather, is the full set of Lagrange multiplier tests, which is highlighted here. So let's run this and see what the output look like. I'm just going to extend the window here so we can see it all. And here is the LM error test. Again, just repeating the basic LM error test that I just executed. And we see that the value is very high and it's statistically significant. And if we look at the basic form of the LM lag test, it's also fairly high and statistically significant. Recalling the flow chart that we discussed in class, you want to first look at the basic forms of both LM tests. If they are both statistically significant, then you move to the robust version of the test. If only one or the other is statistically significant, then you specify that form of the model, and obviously if neither of the basic forms are statistically significant, then you stick with your OLS specification. In this case, both basic forms of the test are statistically significant, so we move to the robust version of both tests. Here are the results for the robust version of the error test. The value is still very high and statistically significant. If we look at the robust version of the lag test, it is very small and no longer statistically significant. So based on these diagnostics here, we would specify a model with a spatial error process following exactly in the footsteps of Messner et al. So our own OLS model and Lagrange multiplier tests lead us down the same route chosen by Messner et al. One interesting point to note here is the results of this mixed effects test here suggests that there are elements of both processes at work which might require a more complex model. Messner et al. Don't address that, and we won't get into it right now except to note it and come back to this in future replications when we encounter this and how we might go about addressing mixed effects when they are diagnosed. So now that the diagnostics have led us to specify a spatial error model, how might we go about doing that? So let's scroll down in our script to step 10 here and specify the spatial error regression for robbery rates. I've got some preliminary notes here that I've highlighted earlier. You might want to check your working directory just in case you're outputting files. But otherwise, this is the basic specification for your spatial error model. The command is error spatial autoregressive linear model, and this is our dependent variable, and we have all of our independent variables. We're referencing our data frame from the shapefile. We've got our weights matrix, our method, and our last set of options. There are some more options if you'd like to look at the help file for this particular command, but this is the basic specification. There are other method options that take more time, but the matrix option is one of the faster methods, so let's just execute this one and see where it takes us. So if we execute the spatial error model, you can see it executes with success on the left here. We can summarize that model, and this is the summary that we would want to compare with the output in table 1. We could capture this output and export as a CSV file or in any other format that we liked, and we could run some diagnostics. We can run some diagnostics here, say a Moran's test on the residuals. If this is no longer statistically significant, then our spatial error specification has captured, has adequately accounted for the spatial autocorrelation in the model. And here we see that the Moran's eye is no longer statistically significant. It's quite small. The value itself is quite small. So in this model, it looks like our spatial error specification has adequately accounted for the spatial autocorrelation. Let's look more closely again, though, at the output of the model and compare that with the the information in table 1. Specifically, let's look at the estimates and significance. So let's bring up table 1 and compare them side by side. So here we see model 1, the east dummy has a negative effect but is not statistically significant, and here east dummy has a negative effect but is not statistically significant. Just summarize this again and see if it comes up. Now we have them in the same column here. And we can see that the south also has a negative effect and is statistically significant, and that matches the published findings. We find that deprivation, urbanism, age structure, and divorce rates all have positive effects and are all statistically significant. In the published results, deprivation, urbanism, divorce, and age structure all also have positive and statistically significant effects. Divorce probably comes closest. It's still very statistically significant, but is probably the least significant. And you can see that also in the reported results. Sex ratio, meanwhile, has a negative effect and is statistically significant as reported in the published results. If we look at the coefficient for the spatial error term lambda, we see that it has a positive effect and is highly statistically significant, and that is the same as the published results. Very close in magnitude as well. We find a coefficient of essentially 0.76, and the published result is 0.766. So that is the first spatial error model, and it looks like an excellent specification, and accounts for the remaining it accounts for the spatial autocorrelation. We could also compare the AIC values. The AIC value of the spatial error model is 255, almost 100 points lower than the AIC value for the OLS model. So that's an excellent improvement in fit. So just by this statistic alone, you would say that the spatial error model fits the data better than the OLS model. And then I would leave it up to you to replicate the spatial error model, the simple spatial error model. Sorry, I'm skipping ahead here. We need to replicate model 2 from table 1. So model 2 is the one that includes the squared term for urbanism. So we're just going to add one more predictor. And that model looks like this. And all we've added is this variable over here, PURB12. That's the squared term for urbanism. If we execute that to create the object SEM2, we can then summarize it. And again, we should see results that are very similar to the ones that were reported earlier. Indeed, if you look through these coefficients, they follow those reported by the authors. We can look maybe specifically at the coefficient for the squared term. It's negative 0.061 in our results, and it's negative 0.062 in the reported results. And lambda increases to 0.816 in the reported results. It also increases in our results to 0.812. One comment on the squared term, we might discuss in class how you might interpret the squared term. There's a substantial literature on interpreting interactive terms in regression analysis, so we might talk about what the substantive meaning is of this interaction term. But looking also at the AIC values here, we can see that the AIC value for the spatial error model, model 2 in table 1, is more than 100%, more than 100 points lower than the AIC value of the OLS model. That's an excellent improvement in fit. Again, just as was the case with model 1. We could also look at the residuals, or do a Moran's test of the residuals of SEM2. And the Moran's I is very small, and it is no longer statistically significant. So in both of our spatial error models for robbery rates, the models appear to have adequately accounted for spatial dependence and adequately captured spatial autocorrelation in the data, and this is excellent news. No? So these spatial error models appear to be much better ways of modeling the data than a simple OLS regression. So I would ask that on your own you use these tools and techniques to replicate the results for assault rates that are reported in Table 2 in Messner et al., and then we can discuss everything together in class. Thank you.